Okay, good afternoon all of you. My screen is visible. Hello. Hello.
Yes, sir.
Screen is visible, no?
Yes, yes.
Yes, sir.
Okay, we'll see the last class we observed these components of HVDC transmission system. I think we stopped somewhere in between. We'll complete that and we'll move on to the planning all these things. In this component, this is the actual HVDC system substation, that is a converter station or maybe inverter station, whatever you call it as, because both is same. That is the advantage of HVDC. Any station can act as a rectifier station or a inverter station. These are the, I already explained this some of the components. The rest we'll see and we'll go to next topic. Like a converter stations, and then converter unit, then converter walls, then converter transformers. So then AC and DC filters, reactive power sources, and then smoothing reactor and HVDC system poles. So these are the some of the topics. Here we can see that DC line arresters and surge capacitor, these are the capacitance. Then DC pole bus, and then reactor, smoothing reactor, and then 12 pulse converter, these are the transformers, and bus bar. So AC filters, then DC line, this is the output line, DC reactor, and then converter unit arrestor. So like that, DC filters, here in this side is a DC filter, because we mentioned here is a AC as well as the DC filters, both we need to use. Converter station and then inverter station, as well as the source side, that is in the sense source side is a AC side, and another one is a load side. Load means here you can say that transmission side, that is a DC, and there we can use it after conversion, we use it as a filter, DC filter. So that is the another one. Like that, we have many component. This we'll discuss one by one. I think we covered up to converter transformers, I think so. So we'll see the AC and DC filters, and then power sources, and then smoothing reactor and all. Now just briefly, converter station, as you know that it will convert AC to DC as well as the DC to AC. We can design the both way, that is either in the rectifier station or in the inverter station mode it can operate. Two terminal DC system has only the two terminals and one HVDC line. So in a line we have two terminals, one is in this rectifier station, another one in the inverter station. Then converter unit, there is AC to DC and vice versa is done in HVDC converter station using three-phase bridge converters. Preferably, I mentioned in the earlier also, instead of using 6 pulse converter, preferably in HVDC transmission they will use as a 12 pulse converter, and based on the voltage rating, all these things will decide that pulse devices, whether you are to connect it in series and parallel operation. Based on that you can configure that number of devices. And modern trends, all these things, what we'll do is to minimize the losses, and what way is a better improvement and power carrying capability we have to increase of in the device by using the modern technique. All this comes under by modification, all that in the olden days, or some cases they will convert existing HVDC system, I mean existing AC system, converted into DC based on whether it is a healthy line or a weak line, and you find the short circuit ratio and you can divide, you can able to conclude whether it is healthy or a weaker AC line. So all these factors will consider to decide whether we are to convert or not. And there is a here a converter station will use as a 3-phase bridge converters, that is a 12 pulse converters and all. This is we call it as a bridge circuit. We'll consider HVDC transmission is a 12 pulse bridge converter is used instead of 6 pulse normally, or 2 6 pulse connected in series. Because you know in 12 pulse also, not only the one device, there is a combination of device will form it as a group of device, that is a one set of device we can consider. This is the thing of converter. You can see this. This is one 6 pulse converter and then another 6 pulse converter connected in a series to form as a 12 pulse converter. So this is a 12 pulse converter unit. You can see that this total set, not only one, here we may use different configurations, in what we call it as a single valve, or 2 or 3 valves are connected in series, that way. Here in general word, we cannot say it is a thyristor, it is a valve aspect. That valve consisting of many number of devices also we can consider. You can give it attendance is not mandatory here. I will download that, even if you not given attendance, or continuously many people are giving attendance. And this converter transformers also, you can see that there is a AC network to DC network or vice versa. Converter transformer converts AC to DC side. In between there is a converter unit will be there. There are two set of 3-phase windings as we observed here. These are the transformer. We can use it in that HVDC system. AC side winding is connected to the AC bus bar, and then valve side winding is connected to the valve bridge. So this is the different. You can see that this winding is connected to the AC side, this winding is connected to the valve. That's what we mentioned here. And these windings are connected in a star and one transformer, and delta in another transformer. There is a phase shift of 30 degrees you need to maintain. There is we can see that in detail of 12 pulse converter operation also. AC side winding, that will come under a second unit. AC side winding of T2 and 3-phase transformers are connected in a star. Their neutral is grounded. That also we notice. The valve side transformer winding is designed to withstand the alternating voltage stress and direct voltage stress from the valve bridge. That is the important notice here. The voltage stress, the device side, in the sense DC side stress, these winding has to be withstand, because the commutation is taking place from the secondary side of the winding. That voltage will make use to turn off the valve. That is only the case here. That device has to withstand for all the stresses. There are increasing the eddy current classes due to the harmonic current, and that is also because of the transformer. There is a iron loss. All these things will take place. And the magnetization in the core of the converter transformer, because of the following reason: the alternating voltage from AC network containing fundamentals and several harmonics. So obviously there is a harmonics will be injected, different order of harmonic. I already mentioned in the introduction class what are the AC harmonics, what are the DC harmonics. All these things are given as a formula. H is equal to NP, and NP plus or minus 1. All these things will given different order of the harmonic. And the direct voltage from valve side terminals also has some harmonics, and that harmonics will affect on this. So that is the reason we have to use all the filtering requirement, AC filter as well as the DC filters. That is the case here. Three different types of filters will use AC filter as well as the DC filter, and that some of the filter names also I will quote here. There is a filter harmonic having the following disadvantage. Harmonics will leads the problem. It causes the interference in the telephone lines, and due to the harmonics, the power loss in the machines and capacitors are connected in the system. The harmonics produce the resonance in a AC circuit, results in a over voltage will takes place, and instability of the converter controllers. And these are the some of the drawbacks, and still there is a harmonics are minimized by using AC, and these are the three types of harmonic filters As I mentioned here, there is a AC filter, DC filter and high frequency filters. The types of filters are explained in this way. AC filters, again there is a one unit, I think fifth unit completely there is a filters. So all the design tuned filter, single tune filter, double tune filter, in details of filters, design filter and calculation, all these things come under the fifth unit. This unit only the components, what are the components are available in a converter station. I am just briefly I am explaining only one or two sentences only, because anyhow all these components separately, suppose converters are there, that will come under second unit, protections are there, that will come under another unit. So all this way, and over voltage protections, like that, the current protections, and then filters requirement, so smoothing reactors, and then control strategies. So all these things may have different in it, but the ones if I use as a converter components, we have to specify all the things, but briefly I'm going to explain what is the component function here. So at this there is a AC filter, RLC circuit connected in between phase and air. We that also we noticed in the bus bar side. I mean AC bus bar side we connected as AC filter, and after converter side we connected as a DC filter. So that is the different types of AC and DC filters we observed. And there is a RLC circuit connected in between phase and earth. Like that we have to connect as a filter. So they offered low impedance to the harmonic frequencies. Thus AC harmonic currents are passed to earth. So both tuned and damped filters are used here, and that design part will come under fifth unit, tuned filter, single tune, double tune, all these things. AC harmonic filter also provides a reactive power requirement for satisfactory operation of a converters, because this filter once if you are using, then what will happen, the reactive power requirement also we need to consider in AC side, but whereas in the DC side that is not required. And DC filters connected between pole bus and then neutral bus. So where we noticed there is a AC filter are connected between the bus and then AC side bus, then earth, that is the so that harmonic will be passed in through the air. But DC side filter is connected pole bus and then neutral bus. It diverts the DC harmonics to the air and prevents them in the entering into the lines. That harmonics will not enter into the line, it will pass through the earth only. Such filter does not required in the reactive power compensation. Only the AC side is reactive power compensation is required, but DC side it is not required. So all these things briefly I already explained. Just once I will scroll like this. And then another one is high frequency filter. So there is a band from 20 kilohertz to 490 kilohertz. You can carrier frequency can use it to filter out this harmonics. Noise also can eliminate, and then generate radio interference noise in the megahertz range frequencies. They also generate radio interference noise, because this high frequency filter can minimize that way also. Minimize the noise and interference with the line carrying communication. So in preferably the high frequency filter will minimize the noise, as well as the interference with line carries communication systems. All these things can avoid. Such filters are placed between the converter transformer and then station AC bus, and where we have to connect, that is given. Another topic is there is a converter valves that we mentioned in the previously. There is a, in all modern HVDC converters they used as a 12 pulse converter unit. So in a 12 pulse converter, total number of valve in each unit is 12, because if you consider as a valve, that valve only 12 pulse, 12 valves, but in turn is a combination is there, series and parallel. But once if I want to draw or represent as a valve voltage, all these things in detail will come under second unit. Each valve, if overlap angle is 10 degrees or 20 degrees or 30 degrees, then what is the valve voltage or what is the output voltage. So all where it is going to jump, everything will come, we will see that in detail, but that is not there in textbooks. Also some of the books they given directly waveform. Suppose you can see in any of the textbook, like Padiyar and all, what they given is suppose if alpha is or mu is equal to this one, alpha is equal to this one, they given straight away waveform. You can see in any of I think second unit they mentioned DC and wall voltage waveforms with different values of alpha. It may be 30 degrees or 60 degrees, and another one is in voltage, in the sense wall voltages, output voltages. Directly they drawn the waveform. But I will show you using the graph how if alpha changes or overlap changes, what are the values, because we need to design the value, particularly if so and so degrees, between this degree to this degree, what is the output voltage, or what is the wall 1 voltage, wall 3 voltage, and what is the pole voltage. Pole voltage means here is a VDC is output, but at positive pole, at the negative pole. So what is the voltage at positive and what is the voltage at a negative pole waveform, and if overlap is beyond 60 degree, what will happen. All analysis in detail we'll see in the second unit. So with overlap and without overlap, both cases are there, and we will try to draw the waveforms for analysis purpose. That is very easy, and only thing is little bit one table we ought to form to draw all these things with different angle. But whereas in case of single phase converters in power electronics, we don't require much complication here. When you want to draw as a wall voltage, every instant we need to memorize, and then you have to plot that. That we'll see in this case. We will see only the 6 pulse converter, but we combine two, we'll get it as a 12 pulse converter. But here is a valve is made up of series connection of the thyristor module. So because one thyristor cannot withstand the total power capability, I mean carrying capability or low demand may not be increased. That's what in the power electronics first unit we discussed series and parallel operation of SCR. In general, we don't require normal application series and parallel operation of SCR, but for very large application like HVDC and all, must and should will use that, because one device cannot withstand to carry that much current. Then to increase the voltage capability and then current capability, we make use of series parallel connection. Preferably for series connection is used for voltage rating, and parallel connection used for current rating. Number of thyristor wall depends on the required voltage across the wall. That's what I mentioned. No? Thyristors, how many we have to connect it in series, all the number is decided by the voltage rating. If we need more voltage, then we need to connect more number of SCR connected in series for voltage rating. And the walls are installed in wall hall. There is a one some case or something like that with using all protection or heat sink, and then cooling also. Lot of cooling mechanism is required here. Even our power electronics lab, if you open the box, a case, if you see that there is a base, heat sinks, and then snubber circuit, and some mesh, some ventilation, all fans also will be there. Once if it is on, some sound will come. That is a backside fan, exhaust fans, something like. But even though for small thing we take care of that much protection, but large power transfer capability of the device, we need to use as a cooling also. For that cool air or oil, something they can use for cooling purpose. This is the 12 pulse converter as I shown earlier. Another one is reactive power source. So the reactive power is required for the operation of the converters, because based on the low demand, all these things, the reactive power compensation is required in the AC side, but not in a DC. AC harmonic filters provide the reactive power, properly. Some extent, but you can use some more filters or fax components to minimize or to control or compensate the reactive power, all these things. Additional supply may be obtained from the shunt capacitors and synchronous phase module modifier and static wire system like SVC, StatCom, all these things. Latest approach, you can use it to compensate the reactive power. The choice is depends upon the control desired how fast we need to react. If you are not acting fastly, the compensation is required voltage will be fall down if it is not meet the demand requirement. So that is the reason we need to decide what is the rate we need to cool it, these things. So what we mentioned is a cooling mechanism and reactive power requirement, whether you have to use SVC or a StatCom, all these things you can decide that. Then smoothing reactor, this is also one of the important. So where we'll use this smoothing reactor after converter. Once if you use as a converter here, then this will be as a like this, we can use as a smoothing reactor for all the cases. Then what will happen after getting output DC? That lower order harmonic will be suppressed mechanism of the control strategy, but higher order harmonic will be there. That magnitude is very less. If we pass that waveform to the inductor, smoothing inductor, then it is going to be nullified. So that is the thing of smoothing reactor. Is an oil filled or oil cooled reactor having a large inductance. So that is only the thing is why this oil cooled or oil filled only for cooling purpose, because all that power has to transmitted through the reactor. So then what will happen? The reactor automatically it will heat it up. So that is the reason the reactor immersed into the oil, so that it will cool, because large current has to carry these reactor. So that is the reason we have to provide as a cooling. It is connected in series with the converter before the DC filter. So after the some cases, very small rating applications, we don't require even DC filter also. Normally only the filter is sufficient, means smoothing reactor is sufficient to suppress that harmonics. But only for high rating and accurate power we need, or you can say that we have to eliminate completely harmonic, all these things only we have to use or design the DC filters. But normal cases for small rating applications, the DC filters are not required, only smoothing reactor is sufficient to filter out that. It can be located either on the line side or in the neutral side. So we can place this device either in the line side or in the neutral side. Preferably in the line side we'll use. Smoothing reactors serve some functions. They smooth the ripple in the direct current. So that is only the purpose actually, because in our case you can see this. This is the way we will get it as a DC output voltage. But what we need to do is we have to smoothen out that. But this is given as a lot ripple, but once if you use as a 12 pulse converter, so you will get it as a, this is the shape of waveform, you will get it. So once we pass this through the what we call it as smoothing reactor, you will get this type of waveform that is little bit in the smoother in nature. They limit the fault current in the DC line, because if any fault is happened also, automatically we can able to minimize that fault current using the reactor. That will not allow sudden changes. Consequent commutation failure in the inverters are prevented by smoothing reactors. So these also are important thing. Once the commutation failure takes place, the before for something is happened, if the reactor is there, it won't come to this side. It will minimize there itself the large current we can minimize, so that we can able to rectify that fault and we can restore the operation. But whereas if the reactor is not there automatically, it is connected to the load side, and load will affect if any commutation failure takes place. So that's what the here smoothing reactor reducing the rate of rise of the DC line in the bridge when the direct voltage of another series connected voltage is collapsed. So if anything is happened, this can withstand some extent. Smoothing reactor reduce the stiffness of the voltage and current surges on the DC line. So reactor is always will not allow sudden changes, so that some stiffness we can reduce some extent, and the stress on the converter values and valve surge diverters are reduced. So surge arresters something we can able to minimize because of the smoothing reactor. You can minimize that side because it will not affect. So some protection you can reduce, so the total cost of that system is going to be minimized. Then system poles, you can see that pole is a part of HVDC system. That's what I mentioned, a positive pole and negative pole like that. All the equipment in HVDC substation, there is a plus side and then minus side. We can see that depends on rating. You can decide. Preferably, all the things are negative. Conductor will use if you are not using as a two conductors. That negative conductor automatically will reduce the corona, all these things once comparatively the positive conductor ionization. Anyhow, corona also will be the one of the topic. This is the last topic of that unit. It is also interconnect the transmission lines which during normal operating condition exhibit the common direct polarity with respect to the earth. That is what poles only, the anyhow that is common thing. There is a positive pole in the after converter station. You can say there is the positive pole and this is a negative pole. That also we noticed in case of HVDC links. Increase the transmission lines which during normal operating condition exhibits the common direct polarity with respect to the earth. So we can take it directly with respect to x as a plus, or you can take this is with respect to earth as a minus. That word referred to pole refers to the path of DC which has the same polarity with respect to the earth. And total pole include substation of pole and the transmission line pole, and that is about the components, whether it is a poles or a converter or a transformer or a valve or AC filter or a DC filter or a smoothing reactor. If the question comes, they explain the components or of HVDC transmission system, then you can elaborate that each and every component briefly and just draw the diagram, that is a converter station diagram, and you can specify all the components very briefly. And then planning for HVDC transmission. Planning must be considered in a DC alternate in a transmission expansion. The factors to be considered are, because once if you want to expand this line, something we have to consider. What are the major factors are, that also we discussed in case of comparison between AC and DC transmission. But while we are planning of expansion or something, some consideration need to consider, as well as the some of the things are depends on voltage level or choice. All these things also will come into the picture, but cost is only the is not a major part, but technical performance and reliability is the major thing. To satisfy this, you can allocate what is the cost. So that is only the major thing is second and third, technical performance as well as the reliability we need to consider. Generally, the last two factors are considered as a constraints to meet. So anything, once if you want to do expansion or any operation, even you can able to withstand some of things are cost, you can able to bear it, but the thing is technical performance as well as the reliability, these things should not be violated. That is a constraint, you have to meet that constraint by minimizing the cost also. That is somewhat you can consider, but finally, technical performance and reliability must meet. Minimum cost option is selected among the various alternatives that meet the specifications. Once if these things are met, then we can able to see that how long we can able to use that cost factor in that area. But technical performance and reliability must be satisfied while you are designing the new converter station or a new transmission line, all these things. But whereas submarine and cable transmission and interconnection of two systems in the different frequencies, obviously we have to select as a DC. Why? Because that already we come across in the comparison side also. Interconnecting systems always DC is a simple one when compared to the AC one, because AC is a frequency problem is there, and whereas DC side we can interconnect simply. And another one is the consideration in the planning for DC depends on the application. When we are planning this based on the application, we have to consider this parameter, how much voltage we have to consider, and how many number of walls you have to connect it in series or in parallel, whether it is required or not. All these aspects is going to be care about depends on the applications. And planning for HVDC transmission, two applications can be considered as respectively. You can see that long distance and bulk power transmission, this also everybody knows, and interconnection between the two adjacent systems. These are the two things we need to consider planning for HVDC transmission. Once the while you are planning means obviously to meet the requirement of your application, that is a long distance and bulk power transmission and interconnection between the two systems. That is only things we need to use. In the first application, either it is a DC and AC alternatives for the same level of system security and reliability, the same power carrying capability. So we can see that in AC transmission and DC transmission, powers are same. But when the power is same, but if you transmit that into the AC, you will get more cost and reliability also less, because three conductors are there, as well as the towers, all equipments, protection equipments are the things. But whereas in the DC side, we can notice that only two conductors are there. So that is the reason for the first application, long distance and bulk power case, we can use directly as a DC transmission, because the reliability factor is very high. I mentioned in the previous classes, like how many years or how many hours it we can withstand the device components or converter station component. That will be as a very very long life, so that reliability will be more. And the cost comparison would be the base of the selection of a DC, whether it is a AC. That is, if the requirement regarding the technical performance are not critical. So in that case, we can see that only the cost aspect. If the technical performance are not critical, then you can see what are the things. So there is a different configurations are there, and the substations are a rectifier inverter station, two terminal DC link. This one is a two terminal DC link, is connected rectifier station and inverter station controllers are there. You can able to connect these two controllers through the DC link, and back to back DC link along with the AC feeder. So there is AC feeder and back to back converter. One converter act as a rectifier and another converter act as a inverter, so that we can use as a back to back connection. Another one is a back to back DC link at a border. So in the only thing is, some cases feeder is near to that or feeder is far away, but whatever we want to do rectifier or inverter depends on our requirement, the distance after traveling that DC power, then only we can use as a what we call it as a DC inverter station. different configurations for asymmetrical interconnection, that is the A is a two terminal DC link or back to back DC link or back to back DC link at border. So all these things is a different configurations are there. And in case of second application, what is the second application? Interconnection. So first application is a long distance bulk power. There the cost will come into the picture, but not much in the technical aspect there. But whereas here in case of second application, AC interconnection poses several problems in certain cases. For the same level of system security requires the capacity of the AC interconnection will be the much more than that of the DC. So the DC will be more secure than the AC. That is also one term, and also in terms of reliability also the same aspect will come into the picture. DC will be the more reliable. Thus the choice of DC interconnection will based on the conditions. That is, one is a small fluctuations in the voltage and frequency do not affect the power, which can be set at any desired value. So that will not affect much. The system security can be enhanced by fast control of a DC power. And then you can see that having settled on the DC link for the interconnection, there are three possible configurations that we see in the previous diagram. Three possible configurations are there. One is a two terminal transmission where each terminal is located at a suitable place. That's what in the three diagrams, first diagram I am telling here. Two terminal transmission where each terminal is located at a suitable place somewhere within the network. So now we can place anywhere in that terminals, substations, or you can say that converter station, and connected by a DC overhead lines or a cable. So, but cable is not that much long distance. It will be used submarine and underground transmission is required. We can use it. Second one is a back-to-back HVDC station located somewhere within a one of the network. So we can see that second diagram, to AC link, we can connect the two in the one network place only, but that is transmitted through AC once if it is converted, and it can back to that of AC and you can transmit one place. AC line from other network to the common station. That's what AC line is also shown in the other network. DC, both the converter station and inverter stations, that's what on the second diagram, if you recall, there is a box here and both is connected in this one network, and other network is a AC. So that is the second case we noticed there. And then a back-to-back station located close to the border between the two stations. This is a special case of the above. So we can see that is a third one. We can use here is a blocks, and back-to-back both will be in the border side. So that is on that network area 1 and network area 2. The choice between the first and second configuration is to be noted that converter costs are less for the common coupling station, and AC line costs are greater than the DC line cost. So why the AC line cost is greater than the DC line cost? Because the two substations are placed as you wish. We can place it near our load side centers, or that depends. So based on that, automatically if once if you use as a DC, will reduce that cost comparatively, so greater than the AC line cost. And another one, if the distance is involved are less than 200 kilometers, the second configuration to be preferred. So if the distance is very less, then what you will do is converter station and rectifier station, both you can place it at the same location or the same network. Then you can take it as AC feeder is the transmission. That's the beauty. In the previous we observed in the cost economic wise also, beyond 500 to 800 kilometers only DC transmission is preferred. But whereas here AC transmission case, if the length is less than the 200 kilometer, then automatically what will happen is both stations you can place it in the very near to that place, so and that can be preferable one. And if the short circuit ratio is acceptable, then the third alternative will be the most economic. So here the short circuit problem also we need to calculate. Anyhow, it will come another slide. The short circuit ratio is greater than 3, let it be, that is a Waker line, all these things, the problem. So we have to consider the short circuit ratio is within an acceptable range, very less values, then you can see that third configuration also we can use it for the economic purpose. Specific and design of a DC system requires an understanding of the various interactions between the DC and AC systems. So there is a specific design require understanding in the various interconnection between AC and DC systems. Some of the specifications are required to design of this interconnection system. Interruption of the power DC link can occur due to the DC line fault, AC system faults. So if any interruption, that is a reduction of power in a DC link can occur, there is a DC line fault due to that, or maybe AC system fault. So during that conditions, there is a DC link power also will reduce. The speed of recovery for the transient DC lines fault is of the concern in the maintaining the integrity of the overall system. There is a how much time taken to recover that fault. Suppose if any fault is occurred during what you call it as a DC line fault or an AC system fault, so, but DC link will be interruption, but if how much time it is fastly recover, that is also major constraint here. So we have to consider that aspect also. The power flow and stability studies are used in this context. So once if the transmission takes place and recover back to that of DC, even DC power flows also there, and all the stability analysis we have to consider. The recovery of DC link from AC system fault is more complex. If the AC side is fault is occurred, that recovery is a complication in terms of the AC link, because AC link may be bidirectional AC link or monopolar, bipolar or homopolar, whatever the link. We can see here there is a thing of if AC fault is occurred, then what will happen, that recovery in the DC link is complicated. And the depression of AC voltage at the inverter bus can lead to the commutation failure and loss of the DC power. So if anything commutation failure, the voltage dip or something is happened in the inverter bus, can lead to the commutation failure. So once commutation failure is what here in terms of the valves, commutation failure is nothing but a valve failure. I mean how the device is appropriately not turn off properly, that leads as a commutation failure or miss failure. All these things will leads as a loss of a DC power. DC power output can lead to the reduction of a AC voltage and failure of commutation, that due to the corresponding increase in the wire demand. So if that is happened, the wire demand will increase, then we have to compensate that reactive power compensation. So that is also the problem. And then an optimum rate of increase in the DC power can be determined from stability study. This is influenced by the control strategy and system characteristics. There is a aspects required the detailed study, because once if you are aware of that some detailed study, the system interconnections or interactions, all these things we need to consider. There is a wire requirement for the converter station, dynamic over voltages, harmonic generation and design of filters. So these following aspects also required in the detailed study of the system interactions. So when the two systems are interconnecting, you need to consider as a wire requirement of the converter station, over voltages as well as the harmonic generation, and that leads as a filtering requirement also. So the designing of filtering also we need to consider. Damping of low frequencies and subsynchronous oscillations we have to consider. So that is the different aspect. Detailed study is analyzed before planning as a new substation or a new line, and carries the frequency interference causes by spike currents. Spike current in the sense with small time duration, you may get very high voltages. So that is due to the discharge of the stray capacitance and snubber circuit, because in the DC transmission side each wall will use as a snubber circuit. All these things, snubber is a very minimum protection in that aspect, but there is a stray capacitance, all these things. It also be in parallel with that of a device. The converter control plays is a major role in the interactions, and control strategy should such a to improve the overall system performance. So to improve the system performance, we have to use as a converter control strategy. Digital simulation and HVDC simulators are used for planning and designing studies. Normally, if anything we want to install or substations, even normal AC substations or anything, forecasting is required normally in for the load studies, all these things why we are using. To do that, what we want to use is here, we'll use preferably as a simulation, and then we'll see that parameters and performance, and then we will install practically. Here also what their intention is, digital simulation and HVDC simulators are used to planning as a design of the studies. So then another one is choice of voltage level. What is the voltage level impact in this is to minimize that cost of a plant to minimum cost, and what are the optimal voltage levels are required, that is also consideration here. You can see that for that long distance bulk power transmission, and the voltage level is chosen to minimize the total cost of a given power level. So what is the total cost include two things, that is a one is the investment cost, another one is a loss. So loss also we have to consider as a cost, because once the power is generated, whether you are utilizing or not, even if it is waste also, there is investment cost is there. So that's why you have to count the two things. Total cost is means sum of the C1 plus C2. C is equal to C1 plus C2, that includes investment cost as well as the cost of loss. The investment cost per unit length as modeled as you can see that there is empirical relation, no proof for this. They given as an empirical relation C1 is equal to A naught plus A1 NV A2 NQ. So A0, A1, A2 are the constants, and these are the some N and V. V is the voltage level with respect to the ground, and number of conductors are the N, and Q is the total cross sectional area of the conductor. So all based on that cross sectional area of the conductor, number of conductor, and what is the voltage level of that conductor. So all these things will decide as a cost. So what is that C1 cost? You can see that C1 cost is an investment, because once that parameter, number of conductors are vary, or the voltage levels are vary, or cross sectional area of that conductor size. So if anything is varies, automatically cost is going to be vary. So that is a cost of a investment. The cost of losses per unit length is given as, there is another formula, empirical relation. This one is a cost of investment, and this is a cost of a loss. So using that, you can see that conductor resistivity and T is the total operating time, because how much time it is operating, that is also influence on the loss. Because if you are operating the transmission line in a particular duration or very specific, then loss will differ. So if you are continuously operating, or it is connected to the system continuously, then the loss will more. So that means that is also number of hours it is operating also is going to be decided. That's why we mentioned that. And total operating time also in years, how many years it is going to operate. And L is a loss load factor, P is a cost per unit generation. So now we can simplify that C2, that is a loss. This is the formula for C2. And now we can see the diagram. It shows as a what is the minimum separation equation, minimum cost. Here this is the voltage level. We can see that line cost as well as the converter cost they consider, and this is the point we got it as optimum converter voltage. If you operate this point, then that is the optimal value of a voltage. And converter cost, we can decide this is the point at converter cost, and this is optimal line voltage, and this one is the optimal converter voltage and operating system voltage. So all these parameters will shows as a what is the voltage level we need to operate to get it as a minimum cost of that thing. So that's what, by considering two things, so choice of C1 plus C2, just for simplification is another. Here you can use as optimal power flow concept to minimize the cost, that is a minimum sum of C1 C2, because equations are there, you can able to minimize that. And finally there is some simplification they made it here. Then total cost C is equal to C1 plus C2. So this is the final conclusions we got it. And voltage level B be chosen minimize the cost of C. So we have to choose this voltage such a way that to get it as a minimum cost. By considering as a investment cost or loss, all these things total cost will minimize by minimizing of the or by consideration of a voltage level. Another one is the selection of optimal system voltage is minimized the sum of the converter and then line cost. That is only the diagram I shown you. In the case of back-to-back DC link, the line costs are absent. So in a back-to-back, what will happen? There is a we observed in the near to the stations. So the transmission line is not be as a lengthy. So the line cost will be absent. Hence the voltage level is chosen to minimize the converter cost. So only you have to choose the voltage such a way that you minimize the converter cost, because no transmission line cost, no losses, because total cost is dividing as a converter cost, I mean investment, like as initial capital installation. Another one is a transmission line losses. So if no line, then automatically line losses also will be minimum. This level is generally much lower than that of the presence of override line. And then we'll move on to the modern, yeah, doing more. So there is a modern trends in DC transmission that we'll see in the next class. So only one more class is required to complete this. After that I will conduct as a slip test. So I will send this PPT all of you. It is very theoretical oriented only first unit. That's why it is not much difficult. Just go through once all these slides and you can write by your own. It is not a complication. You just give it your own sentences, advantage or disadvantage or comparison, technical aspect or planning or modern trends and types of HVDC link. Only these type of questions are there, and then components of HVDC systems. So using that you can simply write your own, but once and twice you can read this theory document, and but next unit onwards all things are logical and something design oriented, all these things, but very simple only. Total HVDC itself is a very simple thing, very small syllabus and all. So now we'll finish it first unit by the next class. If you have any doubt you can ask me, otherwise you can give attendance.